All right. So, gas laws. These are the topics where questions are going to be derived. Okay. Being able to convert between various gas units. Yes, it will be Monday, Tuesday. So I will turn it on for, I don't know, whichever days. It was 2 days. So I was going to turn it on for 2 days. So I don't know if that includes Monday or not. I mean, I can certainly turn it on early, since we're not going to have class on Monday. I can turn it on Monday. So yeah. I mean, I originally had planned on Tuesday to Wednesday, but we can, I can turn it on early. So as soon as I get it written, it's no big deal. So, because like I said, it's the last test. So, I mean, once you get your test done and you've got your research paper in, then conceivably I've got all the stuff to do the grades. And then it's just, I got to wait for all of the tests to cycle in. And like I said, I'm probably going to pull everything off of the Canvas site and then put it into a spreadsheet and then sort out the grades that way. So yeah, I mean, I'll turn it on early. That's no problem. All right. So gas pressure between various gas units. So this is conversion between units like ATM to Pascal, Pascal to torr, torr to kPa. So you have to be able to work between those units. Okay, so this involves usually in the class, I don't give the pressure conversions, but again, presumably you would probably have them. I can probably put them on the equation sheet. So just being able to convert between those various units, because we have to be able to do that for some of the other problems. Okay, Charles law, Boyle's law, combined gas law. These we have the variables for volume, pressure, and temperature. And so we'll look at some of the sample problems again in the PowerPoint here in just a minute. Again, these tend to be very plug and chug. Okay, they generally don't have a lot of variation in how they're put together. You have 3 variables, okay? Whether it's pressure and volume in Boyle's law, volume and temperature in Charles' law, or all 3 for the combined gas law, you're given, if it's pressure and volume, if we're looking at, pressure and volume for Boyle's law, you're given 3 out of the 4 terms. If it's volume and temperature, again, you're given 3 out of the 4 terms. If it's all 3, you'd have 5 out of the 6 terms. And so it's just a matter of setting them up and plugging them into the equation and then multiply and divide. So there's nothing overly complicated here. The only real thing that gets complicated is when they give you a mishmash of units. Okay, so remember that you can't use volume and as liters on one side and milliliters on the other side. Pressure has to be a uniform pressure across the board. It has to be like ATM and ATM, or millimeters of mercury and millimeters of mercury. They have to be the same. Temperature is the only thing in here where it has to be in Kelvin. Okay, so for all of these, temperature has to be in Kelvin, all right, for these to work. All right, but again, they're, as the name implies, they're very simple. Okay, you have 3 out of the 4 terms, you plug them all in, multiply and divide. Okay, the ideal gas law introduces moles into the mix, and from which we can also get things like molecular weight or density of gases. So there's it's all from the one equation, and so usually this one is kind of a giveaway when it involves moles of a gas. Chances are it's ideal gas law. Okay, so the moles is the only one where this is really looking at moles being present, molecular weight or density. Again, there's a separate equation for density. All right, partial pressure. So we have partial pressure and mole fraction. Okay, so we looked at some of these last time, and I'll have another video, if I didn't already post it, looking at I think I posted the one for the mole fraction partial pressure one. So these are, again, for the tests, you saw how the test questions are written. They're generally not overly complicated. So if you're looking at problems from your book, then those problems are generally a little bit more complicated than what we saw for the partial pressure ones, right? Gases and chemical reactions, this is our stoichiometry. Okay, so this is using the molar volume. And so you'll have basically the stoichiometry flowchart that we've been working from, where again, we can look at any of the different variables in our stoichiometry steps, and so the molar volume falls right into line there where you can use it along with everything else. All right, so let's take a quick look here. Sample problems, or what? All right, so again, this first slide here, looking at torr or PSI to millimeters of mercury. This is a pretty straightforward example of what you may have to be able to do. Okay, so converting from one unit to another. And so you need to have some idea of what are the conversion factors between these various units. Okay, so converting PSI to millimeters of mercury, or torr, or ATM, or pascals, those kinds of things. So you should be able to do these kinds of things. All right, and so again, this is 2 steps. So this is probably the more complicated of the two, versus the second problem here, where this is a 2-step as well. So again, 2 steps is probably more complicated. And then here, torr to ATM is just 1 step. Is you're dividing by 760 to convert this to ATM. All right. So again, these are all great examples here. These you should be able to do and understand how these are done. I would expect that test questions wouldn't look too much different than these. Okay. All right, our sample gas law. So when looking at things like Boyle's law, one thing to keep in mind, you should be paying attention to the conceptual, what is the question asking, okay? Because again, in the multiple choice questions, you saw when I went over the tests in the past, I was mostly able to narrow down choices to a 50-50 choice from looking at the conceptual value of the question before I started doing any math, right? So here in Boyle's law, the relationship between pressure and volume are inversely proportional. And so if our pressure is going up, right, so we're applying more pressure, we would expect the volume to go down. And so my answer should be, a lower volume than my first given volume. Again, here's the equation. P1V1 equals P2V2. You're going to be given 3 of these 4 terms. Okay, so, but you could narrow down what your choices are. Sorry. Cool it down. So you can narrow down what your choices are just by applying some of the conceptual values. Okay, if pressure is lowering, we would expect the volume to go up. Okay. Again, example here, very similar to what you might expect to see. Okay. 3 liters of hydrogen at this pressure. What is the volume if the pressure is increased to this? Okay, so we have 3 out of the 4 terms. Let's multiply and divide. Our pressure units are in the same unit, so we don't have to do any conversion to them in advance. Right, so it becomes, like I said, multiply and divide, and then because the pressure is going up, we expect the volume to go down, right, which it does. Okay, again, same kind of stuff here. 3 out of the 4 terms, you're plugging the stuff in and kicking out an answer. All right, Charles' law, same kind of thing here. The conceptual relationship is important to apply first. Temperature and volume are linearly related. So as one of them goes up, the other one goes up. Okay. V1 T1 over V2 or V2 T2. Again, the only consideration here is the temperature has to be in Kelvin. Okay. Similar problem, you'll notice the setup here, the volume and the temperature. What is the temperature at this other volume? The volume is going up from 2.5 to 2.8, so we expect the temperature to go up, right? And so we just have to convert that to temperature or to Kelvin, and so from 273 to 297, so it went up, right? So again, 3 out of the 4 terms. Right. The combined gas law just puts Charles and Boyle's together. Again, there's nothing different here for how these problems are done. It's just really that, you know, you're given more variables to work with. And so, again, the only consideration here is the temperature has to be in Kelvin. Okay. All right. So same thing here. So here we just have more terms. We have volume, but you'll notice here you've got, you know, volume, you got temperature and pressure. You have volume and pressure, and they want to know what is the final temperature. So there's no moles or anything. So it's going to indicate that it's more in the line of the combined gas law versus using the ideal gas law, that kind of stuff. Okay. So we're given the temperature, volume, and pressure. Temperature, we're missing volume and pressure, right? And so it becomes just multiply and divide of all of those terms, and then conversion of our temperature to Celsius. Okay. All right, the ideal gas law, PV equals nRT. R is the gas constant. Again, you'll have the gas constant for the problems, okay? Yeah, temperature is pretty much always going to be in Kelvin. Because you could end up with a 0 degree Celsius, Kelvin is generally the scale that's used. So yeah, so pretty much any temperature, Kelvin is the temperature for the equation. That doesn't necessarily mean that it won't ask you for it in Celsius, which means you just got to convert back and forth. Okay. For the ideal gas law, in this case, the other units also have specific units as well. So the pressure has to be ATM, it has to be liters, and it has to be Kelvin for this. Okay. All right, we're not going to worry about what the actual gas law is. Again, simple thing here, how many moles? So if it's looking for moles, that's probably a good indicator that we're using the PV equals nRT. Okay, and again, these tend to be relatively plug and chug kind of problems. There's not anything too difficult with them. So STP, you should know. You will have to know the ATM and the temperature, right? That it's 1 ATM, 0 degrees Celsius, or 273 Kelvin, because the problems when they're worded are worded like this. A gas occupies this volume and pressure and temperature. What volume will it occupy at standard conditions? So if you don't know what the standard conditions are, then it's hard to fill those in, and it looks like we're missing stuff. And this problem here also presents, now this problem here I would actually solve with the combined gas law. I wouldn't solve it this way in this slide, but this particular slide, this is slide 46. So like I said, you can do this with the combined gas law. Okay, I would do this with the combined gas law, but this slide is, I use this slide to highlight that there is more than one way to solve some of these problems. Okay, so that's really the key takeaway from this particular problem, other than the way it's worded and how it's go about solving it. Okay, so because it's a container, right? The number of moles of gas don't change, and so once you find out how many moles of gas there are in the first condition, then you can use that in the second condition in order to find the volume. But again, the combined gas law already assumes that the moles are constant, so it just takes it out of the equation, right? Like that, you can put this into the combined gas law and you'd get the same answer. All right, there's an equation for density. Okay, so this is just a rearrangement of the ideal gas law. So you have gas, you have mass and volume, the pressure, molecular weight are the constant, and temperature. So this is just a rearrangement of the ideal gas law because we already have moles. So if you put the moles on there and then you multiply by the molecular weight, you get grams, right? So, but if you multiply one side, you multiply the other side, and so the molecular weight shows up in the equation. All right. So the same consideration here. Again, when it says density, this is the only one that has density in it. So you'll have the equation for density. And so plugging these things in, it has the same considerations for the ideal gas law. All right. Partial pressure, again, some of these they can be a little more complicated, but they don't have to be. So we just have to keep in mind some of the considerations here. Things like that the total pressure is the sum of all the partial pressures. The sum of the total moles in the system or the sum of all the individual moles. The relationship where the partial pressure over the total pressure will also equal the ratio of the number of moles over the total moles in the system, right? So we can apply the partial pressure to the through the ideal gas law, okay? So, or you can use the combined, the total value for the ideal gas law. And so there's just a lot of equations, and so it's just a matter of sorting out which ones you need to end up using, okay? We have our mole fraction here. So it's the moles of the component over the total moles gives us the mole fraction. It's like a percentage, right? And so the total pressure in the system times the mole fraction would tell you the individual component of that gas, right? So if I know what my total bill is times my tip, and that tells me my how much or times the percentage that I want to tip, that would tells me what my tip is, right? So this one here usually again is these tend to be a little more complicated than the plug and chug kind of problems, but for the most part, this particular example 12 here is pretty much the kind of problem that you can expect to see. So I mean, maybe not quite this complicated because I mean some of these so in this case we're told the total pressure. Okay, so again, total pressure is given, the volume is given, temperature. We're told the other parts of the neon or the xenon here. So we want to find the resulting xenon part, right? So but you can walk through this slide as to how it goes about doing it. Again, we're trying to get down to the neon. If there's only two gases in the system, one is xenon, the other amount has to be the neon. So that means I need to know what is the things like the total moles in the system, so I could subtract it out, and then I would get the moles of the neon. All right, but most of these are probably going to, at least again for the test, they'll be relatively simple. Let's see if I can find the one that. All right, so. Gas collection over water. Again, this is just the same. It's just taking into account that there's water vapor in there. They would have to give you the vapor pressure of the water. And so it's just subtracting out, right? So you have the total pressure, it's just subtracting out the water. So you just got to take the water out of the system if it's collected over water. Okay. All right, so again, this particular chart's a little bit of a different setup than my right. So this is really the one here. All right. So again, usually you'll remember that I put mass on the top, so mine was written a little bit different, right? But we have the aqueous volume. We use the molarity to find the moles, the balanced equation. Whether you're doing in this case, if we're finding the volume, right, of a gas. You'd have the STP, so the 22.4, the molar volume. Okay, so again, most of these you're likely to see these. So what you're likely to see as a potential problem here is like mass of some component A, finding moles, and then using the balanced equation, and then using STP to find like the amount of gas produced, right? So if you have calcium carbonate, so if we have like 50 grams of calcium carbonate, you know, how much carbon dioxide would you make, right, at STP? So again, this is working through this setup here. Similar kind of problem could be like, you know, the calcium carbonate reacts with, you know, 12 molar, you know, some volume of hydrochloric acid, and how much gas would be produced. And so you have, you know, 1, 2, and 3. So at some point you're going to use this in the stoichiometry problem. Okay, more than likely this is the setup for the stoichiometry rather than this other one here, where this is not at STP. So again, we talked about that one in one of the previous lectures, where if it's not at STP, it has to give you all the other terms, and then this becomes a little more complicated. You probably would not expect to see that particular thing on the test. I think as far as the stoichiometry goes, you're more likely to see where it's at STP, so you can use the molar volume. Okay. Same kind of thing here. So this is a pretty common example. So I would say this is probably very close to the kind of thing you should be able to do. So if you understand this particular problem, then this is probably very close to what you should be able to do for the test, right? So we have 100 grams of a lead oxide, you know, we want to know how much oxygen is produced at STP, right? So starting from the mass, we use the molecular weight, the balanced equation, which I will remember to give you the balanced equation, because I that one problem from the last test was missing a balanced equation, which then if you didn't look it up, it probably would have been hard, which again, we're not supposed to be looking stuff up during the test, but conceivably without the balanced equation that I didn't give you, it would have been very hard to solve that one particular problem. But anyway, so I will make sure that I get those in there this time. All right, so that's it for the gas chapter. Okay, questions on the gas chapter before I move on? Again, you'll have all the equations. So you'll have all the equations, you'll have the gas conversions, the pressure conversions, the constants. So really it just comes down to, you know, do you know how to put that stuff together? Do you know how to plug those things into your calculator and multiply and divide to get out an answer? So conceivably it should be fairly straightforward, okay? Again, the problems in the PowerPoint, I mean, I specifically put these in here because these are the kinds of things that you should be able to do, okay? All right, so let's look at thermodynamics. All right, so I didn't get the thermo video that I was going to do for Hess's law, but I will get that tomorrow, so I will get that posted tomorrow. All right, so here's what we're looking at for our questions for thermodynamics. Okay, heat, energy, and work. Should be able to identify appropriate signs for Q and W. Should be able to calculate internal energy given heat and work. All right, so this first one is super easy, all right? This is just putting the proper sign on the energy values. So these particular problems, again, the relationship between energy and Q and W is Q plus W equals energy, right? Heat plus work equals energy. So you're given two numbers. All you have to do is put the right signs on them. Okay, so we're talking about assigning signs to heat and work based on how the problem is worded. Okay, heat being given off. Okay, heat being given off from the problem, right, means it's negative. Any energy leaving the system means the value is negative. Okay, heat being put into the system, okay, or heat being absorbed by the system means it's positive. Okay, work is always a pushing force. So anytime the volume is expanding, so in pretty much any of the examples, you're looking for expansion. Okay, expansion of the gas means it's negative. Okay, because the gas is pushing out, and so it's expanding. So the volume, so if you remember that for us, work is a pressure and volume term. So as work expands, or as the system does the work, okay, the system being the gas is doing the work by pushing, all right, the value is negative. Okay, so then you just put the two numbers together and add them up. All right. The other thing to consider too, there's one other thing in here, because sometimes these problems get tricky because we're not paying attention, is that the units on heat and work have to be the same. Okay, so just think about that. So if you're looking at joules for work and kilojoules for energy, you can't just put those two together. Okay, so just be mindful of the units that we're actually adding. All right. Enthalpy, so this is, should be able to calculate pressure and work, okay, or pressure, volume, work. So this is there's one equation for work. So again, there's the one consideration for converting that that we'll get to here in a minute. So again, there's an equation that goes with that. Specific heat, should be able to use specific heat to determine change in temperature, or should be able to calculate heat required to change the temperature of a substance. All right, so that again, this is really one equation, okay, Q equals MC delta T, but the specific heat, there's a variety of conceptual problems that we can think about for specific heat by itself, okay, as a term. Like what does specific heat mean when we look at the term, okay? So again, using that one equation for this, again, it's mostly plug and chug. And then the enthalpy of reaction. So there's a little stoichiometry, so it's lesser, it's only 2 steps, again, but the kinds of questions here are, if I give you 50 grams of propane, how much heat is it gonna produce? Okay, so the first step is the molecular weight and then delta H, both of which you're usually given, okay? The second kind of problem is, if I burned propane and it gave off 1,000 kilojoules of heat, how much propane did I start with? So this goes back the other direction. So I'm starting from the amount of heat, and then I go up using the delta H value and then the molecular weight. So it's only 2 steps for the stoichiometry. And then the Hess's law problems. Again, we looked at some of these last time, but at least one of these last time, and I'll look at some additional ones to give you some additional practice on doing those. So you're guaranteed to see those Hess's law problems. Again, they're very unique in how they look, so you're not gonna mistake it for something else. Okay. All right, so let's take a quick look at some of our problems. All right, so where's my problem here? All right, here it is. All right, first equation, okay? Delta E, internal energy, equals Q, the heat, plus the work, W, okay? So just like this problem here, so this problem here is pretty much right on spot. It's missing the star here, so this is, but this is, a flask releases 890 joules of heat, okay? They didn't tell you that the value on that is negative. You have to put that on there. So if it's releasing heat, okay, the energy is going out, okay, the flask is releasing heat, that's negative 890 joules of heat, okay? The surrounding, and the gas performs 450 joules of work on the surrounding. So the gas is doing the work, it's pushing up, okay? It's doing the work, so it too is negative. So both of those signs are negative when you add them together. Okay, and so there you have it, right? Negative 890 plus a negative 450. They didn't tell you what the signs are, you just have to put them on there, okay? That's it. This first one's pretty straightforward, okay? You just got to add the two numbers, but there's a lot of room for mistakes. There's a lot of room for mistakes based on how we read the problem to be giving us the value, right? All right, pressure work, okay? Most of our problems for chemistry deal with things like pistons, okay? So pistons or balloons are our main examples here because we're talking about a system expanding, right, or contracting, and so we have to have that ability to do that. So our pressure is our force, and our change in volume is our distance. Remember, that's the physics definition, is a force pushing over a certain distance is the work, okay? So our pressure here is going to be in ATM, and our volume is going to be in liters. So our only consideration here is that you have to multiply this answer by 101.3 to get it into a joule, okay? Because an ATM liter is not a unit of work, okay? It's not a unit of energy, right? And so you'll see that here. They have the change in volume, they put the two together. So you can almost be guaranteed on the test, there's gonna be a problem that says negative 1.75 joules is the answer. And so that's what showed up on my calculator. I did the math, 1.75, that's it. Okay, just don't forget. ATM liter are the units you're working from. You have to multiply by the 101.3 in order to get the actual units in joules. Okay. Again, these are pretty simple. You have pressure and a change in volume. Those are the only two terms, okay, to be worked. All right. All right, specific heat. So for heat, okay, for the Q value, Q equals MC delta T. Mass is usually in grams. So because the specific heat value is joules per gram degree Celsius, mass is usually in grams. Delta T is usually in degrees Celsius. Okay. We should also know that it doesn't matter if it's Kelvin or not, because the change in temperature, a degree of Kelvin is also a degree of Celsius. Okay. So it's not like Fahrenheit where 1 degree change is not 1 degree change of the other unit. Okay. So, so what you have here first are potential problems where we have conceptual values. Okay, so conceptually, all right. So the problems, if we're looking at a conceptual approach to using heat capacity, maybe if I had aluminum and cobalt and iron, right, and carbon dioxide, if I had 10 grams of each one of those, which one is going to have the highest temperature after applying some amount of energy? Okay, so in some conceptual problems, they don't give you the amounts per se. So they may, if they say 10 grams of everything, so they've given you 1 unit, right? But but the problems may not say how much energy is applied, or they may not say, so you're really looking at, the heat capacity is the real variable, right? So you could say, I'm going to give 100 joules to everything. Okay, if I applied 100 joules to 10 grams of aluminum, 100 joules to 10 grams of cobalt, 100 joules to 10 grams of iron, and 100 joules to 10 grams of carbon dioxide. So you would be able to come up with the value that you want to put in there, because a lot of times conceptual problems, they're just looking, the question may be which one is going to gain the most amount of heat. Okay, so the maximum value is going to be really dependent upon your understanding of the specific heat. So in any problems where they want to know the maximum or the minimum, okay, let's look at this. All right, you have aluminum is 8.9, iron is 0.4, cobalt's 0.4, carbon dioxide is 0.8. If you're looking for the maximum value, there's only 2 of these that are actual answers, okay? Because if I multiply my heat capacity by my mass, and divide by the work, either the biggest number or the smallest number are going to be my two choices, right? So something in the middle is not going to be more, right? So if the answer really depended upon the heat capacity or the specific heat being a low number, right? So then obviously iron would be the lowest number. So you're not going to get a better value out of 0.46 rather than 0.44 if it's trying to get to the bottom number, right? So if it's looking for maximum values, the two numbers, they have to be the extremes, right? They have to be on the extreme. It's either the highest number for the aluminum at 0.89, or it's the lowest number of the iron at 0.42. Okay, so it eliminates out all your other choices out of there. Okay, if it wants to know the maximum heat, it has to be either of the maximum values, either the highest or the lowest, right? And then we have to do some math. Then we have to put the math together and say, okay, well, if I applied 100 joules of energy, okay, and I'm looking for delta T, that means I'm dividing over, okay? So 100 joules divided by 10 divided by my other number. So if I'm dividing by, a number, and again, you can put actual numbers in there. You can try it out. Just you use the same numbers for both trials, right? 100 joules divided by 10 divided by 0.44. 100 joules divided by 10 divided by 0.89, and which number gives you the largest delta T. Okay, so those kinds of conceptual problems, they're not specifically using the problem where you kind of have to fill in the blanks, right? But it depends on how do we understand what specific heat is, which is how much energy does it take to raise its temperature. Okay, so metals, it takes very little amount of energy to raise its temperature. Okay, so if we're looking for a maximum amount of temperature, well, iron has a very low amount of energy to raise its temperature. So that means if I apply the same amount of temperature to all of these, the smallest value, well, in this case, if it was all of these, the gold here is the smallest value, right? So the energy applied to the gold would raise its temperature a huge amount. Okay, so it's about how much energy is required to raise its temperature. So if it's not a lot, if it's a very small number, it means it takes very little energy to raise its temperature. Okay. All right. So, and then the real problems are where you're given the values and we're plugging them in. Q equals MC delta T. So here, this is where your negatives are going to show up, is from the delta T, right? Is your change in temperature. Okay. So if the change in temperature is positive, then your Q value is going to be positive. Okay. All right. So then delta H. So we talked about this one. So again, this is the stoichiometry. So this is just using the delta H value in there, okay, as a second step, right? So this problem here is very representative of what you're going to have to face, okay, what you're going to have to be able to do, right? Is if I'm burning 50 grams of methane, how much heat is produced, okay? From that balanced equation, or from my chart here, if I have the mass of what I'm starting with, the molecular weight to find the moles, and then the delta H value to find the heat, right? So there's the molecular weight, there's the delta H value, okay? Again, the delta H here is per mole in the balanced equation, or as it was brought up last time, it'll tell you that that the value is kilojoules per mole, right? That's the other thing. So if it has a balanced equation, you should be checking the balanced equation. If it doesn't give you a balanced equation, it'll tell you that it's 891 kilojoules per mole, so you wouldn't need to use that, okay? Again, this is a similar problem. This is just adds to the extra complexity of throwing in the kilograms. Okay, here's burning diamond. Again, same setup, molecular weight, delta H, right? I didn't have any examples here, but there, like I said, there is the opposite. There is the opposite kind of problem where, it's, given this much heat, how much fuel did you start with? So it just goes backwards the other way. So it's just, using the delta H value and then the molecular weight to find the amount of fuel. Okay, so like I said, it's just the other two steps the other direction. Okay. All right. And last one is Hess's law. So like I said, so this is multi-step process. Okay, so I think we looked at this problem last time. We looked at this one too. So these two we did, and then I think I did one other one. So again, here, the key for these problems is we want to know what is the delta H value for this, okay? It is somehow a summary of these, right? When you're approaching these, best way to do this is you're working from this one here, okay? So what is the first unique item here? So if I pick copper, just because it's the first one, well, but then which reaction am I starting with? This reaction, or do I start with this reaction? There's copper in both. So copper's not unique, so don't start with it, okay? The CuCl2 is only found here, okay? Remember the two things that you need. You need it to be in the right position, and you need the right amount of it, okay? So I need CuCl2 as a reactant, because this is the reaction I'm looking for. I need it as a reactant, and I need 1 mole of it. So it's in this reaction here, but flip it around, okay? When we flip that reaction around, it changes the sign on delta H. Whatever you do to the reaction, it also does it to the delta H value, okay? Then my second one, I need to get the CuCl, and here it is, CuCl, although I have it in the right spot and the right amount. So the second reaction, there is no change. There's no change to the second reaction, okay? It goes in as the negative 36 kilojoules. And then you just add the two together, okay? Once you've used the reactions twice, everything else cancels out. The extra steps in here are not necessary, okay? Once you've used both reactions once, okay, you can be almost certain that everything else in here is going to cancel itself out properly, okay? These are just extra checking steps, right, that things got rid of or went away as they were supposed to do, okay? That one again. I guess I didn't save it last time. Save it this time. Okay. So that's where your copper comes from in this first one, is because one of them got eliminated over here, okay? The chlorine gas is not present. It gets eliminated, okay? Like I said, so a 3 reaction one, probably a little bit much for the test. Again, I'm testing that you understand the basic dynamics of what this is supposed to be. So if you can demonstrate that you can do it with two reactions, I don't really need to test you on 3 usually, okay? So that's really not necessary. But again, you should do the practice, lots of practice problems, and then as you work through these, you'll be fine, okay? Again, these are not really super difficult. It's just we have to try them a few times, and once you work out what are the dynamics of how they use the problems, then like for example, this last one here, like using this one after you've already kind of used everything, like this is really just a canceling factor, but you have to use all 3 reactions. Okay, you have to use all 3 reactions, and then as they do that, then the extraneous things cancel out, right? Okay. So Questions? Like I said, it'll be 27 questions, multiple choice. Total will be out of 100. Well, it's out of 100, but you can get up to 108. Okay. I said there was one. I will have the one change. So I know there was one person who wanted the grade change. I will take care of that. I will do that tomorrow. Otherwise, like I said, the most part is just getting everything turned in. Okay, so if right, so the okay, so I mean, really, it's about getting everything in. So I mean, I did notice there were quite a few people who are missing things. So, like I said, you've got until Friday, basically, right, to get everything in. Okay, guys, that's when I'm taking the research paper. Okay, so if you have other stuff that you want me to grade, Friday is the day. Okay, I'll post an announcement about it, but Friday is the day. All right, so if you have other stuff, again, take something rather than nothing. Right, don't take a 0 and then hope that like your test grades are enough to get you past that pass fail line. Okay, just because it's pass fail doesn't mean we can slack, right, guys?